In this recording, we're going to explore some exponential models based on percent growth. What I'd like you to do for this oil spill application is read through the given information and then see if you can answer questions 1A, 1B, and 1C. Then play the recording when you're ready. All right, I hope you paused and worked those out. All right, so how large was the spill initially? Well, that's when t equals 0, right? That's always, and when we sub in a 0, that makes this whole factor a 1. So we just have 250. That's our initial amount, our y-intercept. But we need to put a unit on there. Of course, that's square feet. What percent is the oil spill increasing by each hour? Well, we know this is our multiplier, but it's a 1 plus r, right? Because it's a growth. Well, r is 0.15, therefore, and I need to put that in terms of a percent. So that'd be 15%. Finally, interpret the meaning of this statement. A of 6 is 578 square feet. Well, it's A of t. That means t must be 6. So 6 hours, right? Because t is time in hours. And then A represents the area in square feet. Okay, so let's write out what we said. Next question asks us to anticipate how many hours will it take to reach 3,000 square feet. Well, what we saw is it was 6 hours to get to 578 feet, but I can't just divide 578 by 6 and get the rate, right? Because it just doesn't work that way. It's not linear. So what I need to do is, and also there was an initial amount of 250, right? So we had to take that into account. So what we're going to do is look at the table. Let's put this function into our calculator. If you have a calculator, you can play along. Substitute in place of here, we got 250 times 1.15 to the x power. Let's look at our table. All right, so in this table, you see it starts at 250, like we thought. And after 6 hours, it's up to 578. And we can scroll down in our table. And we can see the y value is growing. Not quite to 3,000 yet. All right, so now we're starting to see 3,000 show up. So the question asked to find out how many hours it's going to take to get to 3,000. Well, at 17 hours, it was not quite 3,000. By the 18th hour, it had passed into 3,000. So it says, show some entries in from your table. So I don't need to start from 0 because it wasn't anywhere close to 3,000. Some of these entries around 15, 16, 17, 18, 19, something like that. So I'll start with 16. Okay, so like we said, about 18 hours to reach that 3,000 square feet. Question 2 says, okay, different context. Flock of ducks is growing by 6% per year. It has an initial population or a starting population of 68. How many ducks would we have after 10 years? Let's see if we can set something up. We could certainly make a table where we're showing what we multiplied by each time, or we could start with our function. So our function for exponential growth, we know it's growth because it's growing, right? Keyword there. We said we have our initial amount, and we're multiplying by this growth factor, 1 plus the rate, raised to the t power. So if I'm going to set up a model like that, got our initial amount, 68. I'm going to multiply it by 1 plus, but I need to turn that 6% into an equivalent decimal. So that means R is 0.06 raised to the t, which is in this case 10 years. So I could also just write this as 68 raised to the 1.06. I'm sorry, 68 times 1.06 raised to the 10th power. Again, put that in your calculator. If you know of a scientific calculator, you can still do 1.06 to the 10th power. You probably do that on your phone. Then times 68. And that's going to get you 121.778 ducks, which is pretty close to 122 ducks. All right, before we proceed, let's have you work out question number 3. Play the recording when you're ready. Hopefully you took time to read that one over. If we're speaking about a rate of 3.5%, keep in mind our R value is 0.035, right? Not 0.35, that would be 35%. Our starting balance is 350. Okay, so that means our initial amount, or our P, equals 350, our principal value, if we're speaking about the amount equals the principal times 1 plus R to the t power. And it says, which of the following equations would give us the amount in our account, or the worth of the account, as a function of the number of years? So they've kind of used W here. You can kind of think like they're using different letters, but that's okay. They still have the same function. They're using Y as the number of years. So kind of prejudiced these answers. These couldn't be, right? Because that's linear growth. And we know that in a bank account, you get money for the money you've earned in interest. It compounds the interest, right? It doesn't just keep basing your interest on what you had initially. Your money grows exponentially. So we're down to these first two choices, 1 and 2. Hopefully you looked pretty critically at choice 2 and said, that can't be, that's exponential decay because the base is less than 1. So it looks a lot like choice 1, which would make sense because we knew we'd have a 1.035 as our multiplier. And the P would be 350, and we'd be raising that to the Y power. So it looks like choice 1. For question 4, it talks about radioactive material. Now this is something kind of weird, right? It's tricky to think about, but it happens in science. And this type of material dissipates into the environment. It decays. It goes away at a predictable rate. You kind of think about it this way. There's a box of stuff, okay? And let's say every hour, just for a simple example, it has half as much left. So after an hour, it's down to 50%. After another hour, it's 25% of what it initially have. Another hour, it's half of that, so it's down like to 12.5%. It keeps becoming less and less and less, but by a percentage. And not everything is half in an hour. So this particular substance, this unnamed substance, decays according to this function. So how much was there initially? And hopefully you've had enough experience, even though you haven't had a lot of experience with radioactive decay, to be able to say how much there was initially. And I'm wondering if you can find out how much is decaying per day, and can you interpret this sentence? So see if you can work out A, B, and C, and then play the recording. All right, I hope you paused and worked out. If not, please do that now. Don't just watch me do the math. There's no thinking involved there. All right, so there should have been 450 grams, 450 grams of material initially. You can think about it two ways. It's there. The coefficient is always our initial amount. And when we substitute in 0 for D, this term this factor just becomes a 1, right? So 450 times 1 is 450. What's our percent? Well, that's a little trickier to find out. We know it's decaying, so we have a 1 minus R as our multiplier. So that 1 minus R is equivalent to the 0.88. So what must the amount we're subtracting from 1 be to get to 0.88? All right, so hopefully you realize I'm subtracting R must have been 0.12. 1 minus 0.12 equals 0.88, and that's 12%. All right, and then the last one I asked you to work on is, give an interpretation of this statement. What does it mean, A of 14 equals 75? So after 14 days, because 14 is the D, and D is number of days, 75 represents the amount of grams, and G is just the abbreviation for grams, of the material remains. The final component of the question says, the material is safe to transport once it is less than 5 grams. And we need to find out when that will happen. When's the first day when it will be safe to transport this material? So clearly not 14 days, right? Because at 14 days, there's still 75 grams. So we're going to want to enter this function, 450 times 0.88 to the x power. We'll use x instead of d on our calculator. We'll then look at the table. All right, we need to get down under 5. And it looks like it's not until the 36th day when that will happen. So we're going to be able to transfer that information to our paper table to support our answer. There is another technique. If you're wondering, wow, it's kind of tedious. We're always going to have to use a table to get the answer. There actually is another technique, and it's called logarithms. A log will allow you to get to an unknown exponent directly. But that's a lesson for another day, shall we say. For now, we'll be able to get a decent approximation just by looking at the behavior of the y values, how they're increasing in the table, and getting an approximation. I'm just going to round these to the 10th place. You might say, what gives me the right to round these to the 10th place? Well, really, I'm not interested in the y values. I'm interested in the x values, right? I wanted to know the days. So I really just need to figure out which one of these x values is going to get me under the 5 grams. 35 days, still over 5 grams, so right here. So then we can write a little sentence to answer our question. We can say something like, the material will be safe to transport on the 36th day. Thanks for watching.